Polaritons are at the forefront of research in solid-state physics. They exhibit many intriguing phenomena, such as superfluidity and condensation. Polaritons offer unique possibilities to study quantum physics. In this video, we will discuss what polaritons are and how they acquire their remarkable properties. Think about a guitar. This is a simple mechanical resonator. When the string is hit, it starts to oscillate and produces sound waves with a characteristic frequency, or pitch. These resonant frequencies, as they are called, are the ones for which exactly a whole number of oscillations fit between the clamped points. For waves with other frequencies, the string tries to move at the points where it is clamped down, and the waves quickly become very weak. Only waves at the resonant frequencies can survive on the string. Just like the sound waves on the guitar string, light can also be thought of as a wave. Each color of light has a different frequency, and every frequency corresponds to a different wavelength, which is the distance between the neighboring peaks of the wave. Visible light has wavelengths ranging from 450 to 700 nanometers, a size smaller than 1,000th of a millimeter. Now imagine two parallel mirrors facing each other. This is an optical resonator. It confines light inside by making it bounce between the mirrors. The light waves are trapped in a similar way to the sound waves of the guitar string being trapped between the two clamps. As a result, only some frequencies will be resonant and able to survive between the two mirrors. The smallest possible resonator is the one where only half of the wave fits between the mirrors. The wavelength of light is less than a micrometer, so an optical resonator that confines less than several wavelengths of visible light is therefore called a microresonator. To make a polariton, we need to add something to the light. In between the mirrors, we place a quantum well, which is only a few tens of atoms thick. It is called a well because it traps electrons in its plane so that they cannot escape to the surrounding regions. If a light wave with the right frequency passes through a quantum well, it can give up its energy to release an electron from the atom it is bound to, creating a vacancy. Relative to the surroundings, this vacancy is positively charged and is called a hole. Since the electron and hole have opposite charges, they attract and for a while orbit around each other. This behavior forms a new particle, which we call an exciton. Eventually, the exciton recombines when the electron falls back into the hole. The energy is released as a light wave with the same frequency as the one which originally created the exciton. The quantum well is then placed in the plane that intersects the peak of the light wave. So, when the microresonator is calibrated so the resonant light wave and the exciton have the same energy, a single exciton can be converted into a light wave, which then converts into an exciton, and so on. The resonant optical cavity can trap the light wave emitted by the exciton so that it returns and creates another exciton, which also decays. A repeating cycle between light wave and exciton is made possible. Since the exciton and light are constantly interchanging, they behave overall like a new particle called a polariton, which has some of the properties of each.